Okay, so now that we understand what entropy is and kind of evaluating if it will increase or decrease for a system, let's talk about how that's incorporated into our understanding of equilibrium. So if you recall, when we looked at equilibrium, we know that naturally equilibrium will happen in a closed system with a certain percent yield, right? So let's say you might have 10% yield, which means that the reactants are favored, but you still have an established equilibrium. So remember, anywhere from that 1 to 99% yield, even though the rate of the forward and reverse reaction are equal, you may not have, 50% product, 50% reactants at that moment in time. So there are two kind of natural drives that will influence how that percent yield is determined, I guess, or the reason why it is what it is. The first is that reactions tend to favor a decrease in enthalpy. So meaning, decrease, remember if enthalpy is decreasing, let's say we have a negative enthalpy change, that means that we have an exothermic process. So in other words, the reaction will be favored in the direction that will produce energy as a result. So in other words, the exothermic process will be favored. Now, in terms of entropy, the second natural drive is towards an increase in entropy or having a more disordered system. So naturally, maybe you've even heard of this saying, sometimes they'll say, the universe will naturally move towards chaos. And that's just kind of talking about one of the thermodynamic laws that natural processes tend to increase in disorder. So not always, but that's just, what it tends to favor. So there's kind of three scenarios that are going to end up happening. And we actually talked about these three scenarios based on percentage yield. So we talked about going to completion, which means you have more than 99% yield. We have the scenario where it does not occur, which means less than 1% yield. And then, of course, we have an established equilibrium, which is the in-between. Now, the reasoning behind why those happen is because of those two drives of enthalpy and entropy. So if both of those natural drives favor the forward direction, it will tend to drive to completion. If both of the directions are in the reverse, which is obviously the reactant side, then so little product will be made that we could basically consider it that it did not even occur. And then, of course, if we have a system where one of those natural drives is going in the forward favoring and one is in the reverse, that's where we have our equilibrium being established. Now, it may not, again, like I said, it may not be equal in terms of its favoring. That's why we have such a wide range here. But you have really both rates that are happening, right? And of course, just a term that you may see as you come across some of the questions here. The term spontaneous essentially means, like if it says, the following spontaneous reaction happens, blah, 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 blah. Just to kind of make sure you understand that means that it's a reaction that will happen or a process that happens naturally on its own. So it doesn't have to be heated. We don't have to add something for it to get started. Basically, the chemical system, as soon as you add the reactants together, the reaction begins to proceed, okay? Now, we can change the amount that it will react based on the factors we learned about in Chapter 1, but the point is that the reaction will still happen. It might be slow, but it's still occurring. So chemical systems will move spontaneously towards equilibrium, assuming all conditions are met, which is referring to our two natural drives as well as it being a closed system, right? The same conditions we talked about for equilibrium beforehand. So we have some practice problems here where we're looking at essentially predicting, will the reaction have equilibrium? Will it go to completion or not occur? So it's asking us to basically determine which of those three scenarios will this fall under. So there are three that you are doing this for. Practice problem 1, 2, and 3. So if you want to try these 3 out in your book, pause the video, give it a try, and then continue watching. And we'll see where how you do. Okay, so let's look at entropy first. So this one is pretty straightforward. We have 3 moles of gas versus 2 moles of gas. So the increase in entropy is actually in the reverse, right? We have more disorder or more randomness happening on the reactant side. So our entropy is going to the left. And it looks like our forward reaction is endothermic, which means, remember, we're always looking towards the exothermic process as the one that is the drive or the driven force. So if the forward is endothermic, that would tell us that the reverse is exothermic, right? The reverse reaction is always the opposite signage. So that would really be negative 285. So actually, in this case, of the 3 scenarios, we could say that this would not occur because both the entropy and enthalpy are going favoring the reverse. Okay, so let's look at number 2. So it's all the same thing. So we want to know, the following reaction establishes an equilibrium with a reasonable proportion. State whether this is endothermic or exothermic. So this is a little bit different. Instead of them saying which of the scenarios there are, it's actually telling us that this is in equilibrium. So that means that one has to favor the forward and one is going to have to favor the reverse. So they're asking us if this reaction is endothermic or exothermic. So essentially, by determining what's going on with our entropy, we should be able to determine what is happening for the opposite, for the enthalpy, right? Okay, so let's take a look. So gas moles, we have 2 versus 2. Uh-oh. So now we have to look at the where the elements are kind of located. So here we have nothing is a solid becoming a gas. So we're looking at literally just the atom placements. So I would say, if you remember that if atoms are grouped together, they are considered to have less disorder. So on this side, we have H2, so hydrogen atoms by itself. But on the product side, we have hydrogen interacting with oxygen atoms. So I would actually say the product side has more order because the H2 atoms are kind of by themselves versus how they were on the reactant side. So this would be more disorder. The particles are less ordered. So the increase in entropy would be the reverse reaction, right? So there is more disorder on the reactant side versus the product side. So if that's the case, and we know that we need to have enthalpy to favor the opposite, that would tell us that this is an exothermic process, right? So if this had said, let's say it said this scenario is not occurring, then we know that delta H would have to be the reverse, which would have made this endothermic. But in this case, it's going to be exothermic because we need one going the other way. Okay, so number 3. So here we have the following equilibrium has a reasonable proportion. Okay, so that means that we are between that 1 and 99%. State whether the entropy increases or decreases during the forward reaction. So I just want to make something clear. So this one did not say state the forward reaction if it was endothermic or exothermic. If it's not asking you specifically about the direction of the reaction, you are always assuming that we are discussing the forward reaction. Okay? So in this case, I mean, they're being more clear about it. But even if this just had said, state whether entropy increases or decreases, and they did not give us this part, it is assumed to be the forward reaction, just naturally, okay? So, let's go back to this. So here we have equilibrium, so we know that's going to go in opposite ways. And it says delta H is exothermic, negative 518. So that tells me delta H is favoring the forward reaction. So actually, without even looking at elements or anything like that, I can automatically tell you that my entropy is going to be decreasing in the forward reaction because it's favoring the reverse. So entropy is decreasing in the forward reaction. Okay, and that's pretty much it. So the main ideas behind this whole section is obviously understanding what entropy is and if it's increasing or decreasing, and then relating that towards the relationship with enthalpy and having an established equilibrium.